Now let us do Young's double slit experiment, uh, abbreviated as YDS, Young's double slit experiment. Let M, a cardboard having a slit. A slit means a narrow opening, like a pinhole. This is your M, a cardboard having a slit, a narrow opening. That narrow opening is here. And behind that, this S is a source of light. And again, N, another cardboard having two slits, S1 and S2. N, this is another cardboard having one slit, narrow opening here and another narrow opening here. Very narrow, like a pinhole, through which light can pass through, of course. Small d is equal to distance between S1 and S2. S1, S2, this distance, which I have represented here as small d. Now S is a source of monochromatic light. Monochromatic means of single wavelength, either red or green or blue. It is just kept behind the cardboard M here. So light from this source will pass through this slit in all directions, and the light that is arriving here and the light that is arriving here from this slit S1, it will again travel to this side. From slit S2 also the light will travel to this side. Now capital D is the distance of a screen from S1 and S2. At a distance capital D, here I have kept a screen, white screen. Let us see why I have kept it here. Now the light wave traveling from S1 to this direction, it is traveling in all directions, in this direction, in this direction, in this direction, in all directions. Similarly, the light from the source slit S2 is also traveling in all directions. Suppose I consider a point P, a point on the screen. This distance is D, this point is O, this is exactly in between, this O is exactly in between S1 and S2, right? From here at a distance Y, I consider a point P here. Now, the wave from the slit S1 while reaching P is traveling this distance in the form of a wave. So, S1P is the distance traveled by the wave to reach P. Similarly, S2P is the distance traveled by the wave to reach at P. This one is traveling a distance S1P. The wave from here, which is to arrive at P, is traveling a distance S2P. Now look which distance is more. So S2P is longer than S1P. S2P is greater than S1P. So this wave is traveling a large distance as compared to this wave. Now what is happening here on the screen is which part of this wave and which part of this wave, which part of this wave and which part of this wave are combining here. Means this is the wave traveling from here, this is the another wave traveling from here. Now which part of this wave, this part or this part or this part, is combining with which part of this wave? So accordingly we'll find out whether this point is a bright spot or a dark spot. If this point combines with this point, this amplitude and this amplitude, they are in the same direction, so they will be added. So here we will have a maximum brightness called a bright fringe or called constructive interference. If this point combines with this point, this is downward, this is upward, so the amplitudes will be subtracted. So here we will have a minimum intensity of light. Let us calculate it mathematically, right? Now let us calculate it mathematically. Now let me fold it because I have to go to the other page. Now look, now what we have to do is Mark a point A. This point is A on S2P, such that this distance S1P and from AP, S1P and AP are equal. S1P and AP are equal. So by doing so, we conclude that this distance from S to A, this is the extra distance traveled by this wave while arriving at P as compared to this wave. This is the extra distance traveled. That distance is nothing but a path. So this I designate as delta P, the path difference between this wave and this wave. This is the extra path traveled by this wave as compared to this wave while arriving at P. So S2A, I write it as delta P, say is the extra distance traveled by the wave from S2 as compared to the wave from S1 in reaching P, which I explained to you. Therefore, delta P is called the path difference between the two waves. This wave and this wave, the path difference is this. This is the extra path traveled by this wave as compared to this wave. Now let us calculate how much is that. Now, in triangle S2AS1, if I take this angle as theta, this is 90 here, so your sine theta will be perpendicular over hypotenuse. That is equal to S2A over, I am taking the sine of this angle, so perpendicular is this, S2A over S1S2, because this side is opposite to the 90 degrees, is the hypotenuse. So that is same thing as delta P over D, because from here to here is D. Now by cross multiplying these two, I get delta P is equal to D sine theta. I'll make it equation 1. Let Q is the midpoint of S1S2. Let Q is the midpoint of S1S2. And QO is the perpendicular bisector of S1S2. S1S2 is the perpendicular bisector. And then for D very greater than small d, if this is large as compared to the distance between S1 and S2, that is D, then angle PQO, that is this angle, will be equal to angle S2 S1A theta. So if this is theta, this will also be theta. Now in triangle PQO, tan of this angle, tan theta, will be equal to this distance by this distance, perpendicular by base. This distance I have considered it as y, so y over from here to here is a d, which I have mentioned here. So tan theta is y over d. Now, so cross multiplying this, you get y is equal to d tan theta. And since tan theta for small angles, tan theta is nearly theta, sin theta is nearly theta. So for substitute for tan theta, I can substitute sin theta. So times tan theta, I substitute sin theta because thetas are small. Why thetas are small? Because if the screen is very far off, then this angle will be small. Now so by cross multiplying these two, I get sin theta is equal to y over d. Now we have just derived the path difference between the two waves, delta P was equal to d sin theta. D I keep it as d, and sin theta I just derived y over d, so I put it here. So this, so y d over d. I'm not writing, don't think it is dy, differentiation of y, don't think that way. D is a distance. So y d over d. Now I cross multiply, so the path difference delta p is y d over d. Path difference is y d over d. Means the extra path this wave travels as compared to this wave is this from here to here, which is delta p, that is found out as y d over d. That is found out as y d over d, y small d over capital D. Now we know lambda is equivalent to this much angle, which I explained in the previous video. That is, this distance is lambda, and this angle, full angle, is equal to 2 pi. So lambda is equivalent to 2 pi. So unit path difference will be equal to 2 pi over lambda. And here the path difference is y d over d. So this will be equivalent to this into y d over d. So this much path is equivalent to this much angle called phase. And for constructive interference, in the previous lesson we had derived, for constructive interference this phase difference should be n times 2 pi, because under this condition your cos phi was maximum, and therefore the interference was constructive. So for n is equal to, you can put n is equal to 0, 1, 2, 3, so on. So now this 2 pi cancels. So I am left with y d over lambda d is equal to n, where n is like this. Now cross multiplying y, I get n times lambda capital D over small d. Now what is y? Y, the distance y is measured from here up to the point P. Means at this distance y, for constructive interference, means where the intensity will be maximum, y is given by this. So let us put them. So for n is equal to 0, I put it 0. 0 into this thing is 0. So for n is equal to 0, y is equal to 0. Y is equal to 0 means this point. So this point is at this point. Means the wave from here and the wave from here, when they arrive here, they are of course arriving at all points. The wave from here and the wave from, they are arriving at all points on the screen. So when they are arriving at O, this point has a constructive interference, means intensity is maximum at y is 0. Then put n is equal to 1 here. So 1 into lambda d by d becomes lambda d by d. The second position for n is equal to 2, put n is equal to 2 here. So y is this much. So again for n is equal to 3, put 3 here, y is equal to this. So these are the places, this place at y is this place, this place, this place, this place. These are the positions on the screen where constructive interference is taking place. Means there is a bright spot there. So that is what I have explained here. Now if this point is same thing as this is your screen, the same screen. Let me tilt it like this. From here to this side is y. So from here to this side is y. This point is y is 0 at a distance lambda d by d for n is equal to 1. For n is equal to 1 at a distance lambda d by d, means this point is, the intensity is maximum. To this side is intensity. Look, the intensity is maximum at this point. Again for n is equal to 2, y comes out to be this, 2 times lambda capital D over D. So if from here to here is lambda capital D over D, then from here to here, then from O to this point will be 2 times that. Again at this point the intensity is maximum. The intensity is maximum. To this side is intensity. is maximum. And of course the wave from here and wave from here are also traveling to this side. So on the screen at certain points at the same distance we'll also have a bright spot. So from here to here at the same distance, lambda capital D over small d, here again the intensity is maximum. Again at 2 lambda capital D over d, again the intensity is maximum. I have taken a negative sign here because if you consider this y-axis, this side is positive, this side is negative. This negative means towards this side, This positive means towards this side. So these are the places where, these are the places on the screen, where intensity is maximum. That is called constructive interference. Now then comes your destructive interference. Now destructive interference. We derived the path difference between S1P and S2P. S1P and S2P is this much, was derived as this. A path difference of YD by D is equivalent to this much phase difference. That also I explained right now. Right here. Lambda is equivalent to this, unit distance is equivalent to this, therefore YD by capital D is equivalent to this much of phase angle. So path difference was converted to phase angle like this. And we also know when two waves combine, the resultant intensity is given by intensity of the first one, intensity of the second one, plus 2 times intensity of first one, second one, square root of that cos phi. Now, if this thing is minimum, then this I will be minimum. And I will be minimum if cos phi is minus 1. That is, for phi is equal to this. Look, under this condition, your cos phi will be minus 1 for n is equal to 0, 1, 2, 3. Let us check. For n is equal to 0, this becomes 0, 1 into pi. So phi is equal to pi. And the value of cos pi is equal to minus 1. For n is equal to 1, this becomes 2 into 1, 2 plus 1, 3 pi. Pi, 2 pi, 3 pi, again the same point. So the cos value is again minus 1. For n is equal to 2, 2 2's are 4 plus 1, 5 pi. Pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, again the same place. So the cos value is equal to minus 1. So under this condition, the intensity is maximum. And the phase difference we have found out. We converted this path difference to phase difference. So this should satisfy this condition to give minimum intensity. So this 2 pi by lambda YD by D is equal to 2n plus 1 pi. Now pi cancels. I am left with y is equal to lambda capital D comes to this side, to the numerator. 2d comes to the denominator on this side. So the y given by this gives you the places on the screen where the intensity is equal to minimum, starting with n is equal to 0, 1, 2, 3. So let us put n is equal to 0. So for n is equal to 0, this becomes 0. So lambda capital D over 2d. So y is equal to lambda capital D over 2d is the first position. Then for n is equal to 1, put 1 here, 2 plus 1, 3 lambda capital D over 2d. So y is equal to 3 lambda capital D over 2d is the second position. For n is equal to 2, put n is equal to 2 here. So 4 plus 1, 5 lambda capital D over 2d. So this is the position where the intensity is minimum. So this is the position of dark fringes. Means for this point y is 0. From here at a distance lambda d by 2d, there is a destructive interference, means intensity is minimum to this side as well as to this side. Then from here at a distance 3 lambda capital D over 2D, again there is a destructive interference, means the intensity is minimum. Similarly, at y is equal to 5 lambda capital D over 2D is a third position. That is what I have explained here. Let us tilt it. Let us tilt it diagram. From here, at a distance lambda capital D over 2D, right? Lambda capital D over 2D. From here to here was lambda capital D over small d. Now half of that. So this point is lambda capital D over 2D. Here the intensity is minimum. Look, the intensity is increasing to this side. Here the intensity is this much. Here the intensity is 0. So at this point the intensity is minimum. Similarly, this point, this point, this point, and to this side, this point, this point, this point. These are the positions on the screen where the intensity is minimum due to a destructive interference. The video will be little lengthy. Now, a few more minutes. Then comes the fringe width. Now, on the screen we find certain places where the intensity is maximum, like this, and like this, and like this, the intensity is maximum, and certain places where the intensity is minimum, that is here, 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 and here. Now, fringe width, it is the distance between two consecutive bright fringes. Look here, this point is bright. Again, this point is bright. What is the distance from here to here? So we know bright fringes, fringe means pattern. Bright fringes are formed at y is equal to 0, lambda d by small d, then 2 times that, 3 times that, 4 times that. These were the places where bright fringes were formed. Just I explained you before. For the constructive interference, putting n is equal to 0, 1, 2, 3. These are the different places on which bright fringes were formed. So these are the places bright fringes are formed. The center one, when y is equal to 0, is bright. Then again bright. Then at this point again bright. Then at this point again bright. Then at this point again bright. All measured from the point. All measured from the point O. But the naming is like this. Look. This one is called the central bright fringe. This is called the first, this is called the second, this is called the third, this is called the fourth. This one is called the central. The bright spot here, that is here on the screen, is called the central. And then this is called first bright fringe, second, third bright, fourth. So what is the two consecutive? So this minus this is this. Also this minus this is also this. Also this minus this, also this. Also this minus this, also this. Means all bright fringes are of equal width. That is called the fringe width. That is equal to lambda capital D over small d. Now intensity variation. How the intensity changes? Let the two slits S1, S2 are identical. Means the slit S1 and slit S2, the opening here and the opening here are exactly same. So the amplitude coming from here and the amplitude coming from here are equal. So let the two slits S1, S2 are identical. Therefore, I1 intensity, I2 intensity are equal. Let it be I. Now we know resultant intensity after superposition was given by this. If the intensities from slit S1 and S2 are equal and both equal to I, so for I1 I put I, for I2 I put I, so I square cos phi. So this becomes 2I, this becomes 2I cos phi. So I take 2I common, I am left with 1 plus cos phi. So 2I, 1 plus, I can rewrite this phi as 2 into phi by 2. I do it so because I am to put it into a formula. So 2y remains as same, 1, 1. So this comes under the formula cos of 2 theta is equal to 2 cos square theta minus 1. So 2 cos square 5 by 2 minus 1, I open the bracket. So this one cancels. 2 into 2, 4. 4i cos square 5 by 2. So the resultant intensity is 2y 2 cos square 5 by 2, that is 4i cos square 5 by 2. This is the resultant intensity if the intensity is coming from S1 and S2 are equal and both are equal to y. Under that case only. Now in that case, for bright fringes, we know this was the condition where n is equal to this. So this becomes, so put n is equal to 0 here. So this becomes phi becomes 0. So 0 by something is 0. So cos 0 is equal to 1. Square of 1 is 1. 1 into 4i is 4i. If you put n is equal to 1, 2 into 1, 2 pi. So instead of phi here you write 2 pi divided by 2 cos square, 2 cancels. So is equal to cos square pi, that is equal to cos pi whole square. That is again 1. That is square of this again 1. So 1 into this 4i is 4i. So if the two slits are giving equal intensities, then on interference the resultant intensity is 4i for bright fringes. Means the places where bright fringes were formed, at that point the intensity is 4i. Now what about dark fringes? For dark fringes the condition phase difference was this, where n is equal to this. Now so let us put it here. So for n is equal to 0, this becomes 0 plus 1 pi, and cos, so phi is equal to pi over 2, that is 90. Cos 90 is 0 square 0, so 4i into 0 is 0. If you put n is equal to 1, 2 into 1, 2 plus 1, 3 pi. Phi is equal to 3 pi. Now put it here, phi for 3 pi by 2, square of that also becomes 0. So the resultant intensity is 0. So if the intensity from slit S1 and slit S2 are identical, if I1 is equal to I2 is equal to I, then the places at which maximum intensity was formed, that is constructive interference, all will have a 4i intensity, and the places where minimum intensity was formed, they will have 0 intensity. Means if the intensity from here and here are equal, here this will correspond to intensity 4i, this will correspond to intensity 4i, this will correspond to intensity 4i, this is also 4i, here 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 also 4i. But the minimum here, the intensity will be 0. So all other points excepting these points, this, all other points will have intensity between 0 and 4i.